Pre-calculus students, these are the notes for section 8.2, which starts talking about ellipses. And as I had mentioned in class, ellipses is the fancy math name for an oval. So we're looking at ovals more closely. Again, what we're trying to do is break it down, see the math, how these ovals are formed, but we're going to get used to calling them ellipses. So we will be able to understand the geometry of ellipses and their key features, write equations for ellipses, translate an ellipse, and then on Monday we'll work on understand applications of ellipses. So the key here is putting the fact that we're using algebra with a geometry shape together at the same time. Geometry of an ellipse. An ellipse is a set of all points in a plane whose distances from two fixed points in the plane have a common constant sum. The fixed points are called the foci, and that is the plural of focus of the ellipse. So when you go down and look at this picture, you see here's this oval, this ellipse, and it actually doesn't just have just one focus, it has two foci inside it. And you can't help but notice that the center is right between those two, and that outside we get what's called a vertex. But those are all on the same axis, the center and the focus and the vertex. So the fixed points are called the foci. The line through the foci is the focal axis. So we have a center, two foci, and two vertices all on the focal axis. The point on the focal axis midway between those foci is, of course, the center. And the points where the ellipse actually intercepts its axis, those are the vertices of the ellipse. So all of those are on the major axis, which is called the focal axis. And in the second drawing, they help us by showing us that this distance from the foci to a point on the ellipse will always sum to the exact same amount. It doesn't matter if I pick a point down here, up here. The distance to the foci, when we add those together, will remain constant. So that's what this is saying down here. Distance 1 plus distance 2 will be constant no matter what point we pick. That's what forms the ellipse, and that's why it says underneath, structure of an ellipse. The sum of the distances from the foci to each point on the ellipse is a constant. So it gets me thinking, the formula must have a plus in it somewhere, because they keep mentioning that that distance, that sum of those two distances is going to stay constant, and it does. So here's the standard form for an ellipse. Now, typically a horizontal major axis is considered standard. And when that happens, we want to pay attention to where the letters go in the formula. And it's x squared over a squared plus y squared over b squared. So I notice that x and y are in alphabetical order, and so are a and b. And they always equal 1. So we have two fractions, x squared over a squared, y squared over b squared. Here's that sum that they were talking about, and it will always equal 1. Now, I also want to compare and contrast that to what's going on over here with a vertical focal or major axis. So notice this one is longer up and down than it is wide. And I look at the formula and I realize, oh, they switched around the positions for a and b. So with this one, it's x squared over b squared plus y squared over a squared equals 1. And then, hopefully you're saying to yourself, well, how am I going to know which one's A and which one is B? Well, this is something that occurs specially only with an ellipse, and that is the A value is always the bigger of the two numbers. So A squared will always be bigger than B squared. So we're going to know where A is by trying to look at the denominators and saying, okay, which of these is the larger of the two? Now, there are pieces that we need to be able to find, and one of those pieces is going to be C. And when you look at the formulas themselves, you notice that there isn't a C there. C is the distance from our center to the foci. And so to find it, it's easy to remember that the formulas that start for an ellipse with addition, if we have something that's missing, then we'd have to use subtraction to find it. So c squared is going to equal a squared minus b squared. And in fact, it just is using the Pythagorean theorem to figure out what c is. If you look at our little triangle here that has a hypotenuse of a, we would have c squared plus b squared equals a squared. And then if we solve that for c, we see that the subtraction comes to b. So now, I'm thinking about how to graph what I have for an ellipse, and I realize, well, if I know these points, then I can graph it. Anything else is extra. You know, if I find where the center is, that obviously would be an important piece. But they could ask me about the foci, and I could just use the formula c squared equals a squared minus b squared to get those. So, what are these things called? Well, these are the vertices for the horizontal ellipse. And these are the vertices for the vertical ellipse. The others are called covertices. It's like the vertices give us how long it is, and the covertices give us how wide. And covertices finish off that graphing of the ellipse for us, because if we know where the vertices are and the covertices are, well, then we can graph our ellipse. So that's a lot to grab onto, but remember, a will always be the bigger of the two numbers, and if it's under the x squared term, then it's a horizontal ellipse. And if it is under the y squared term, then it is a vertical ellipse. So ellipse is centered at the origin with foci on the x-axis and the y-axis, and in each case a right triangle illustrates the Pythagorean relationship. So because ellipses have a plus in their formula, if anything's missing, it's c squared equals a squared minus b squared. And here's the really key point with ellipses. Always ask yourself, is that bigger value, which is a, is that under the x or is that under the y? Because if it's under the x, then we have a horizontal ellipse. If it's under the y, then we have a vertical ellipse. So some definitions. We've got a line segment with endpoints on the ellipse, and that, of course, is a chord. We talked about chords with parabolas because we needed that for the focal width, and in this case, it's going to help us joining those endpoints on the ellipse. And then a major axis is the chord lying on the focal axis, and its length is 2a. So from vertex to vertex, a distance of 2a. And then we call the other the minor axis. This is where the covertices are. So the chord through the center perpendicular to the focal axis with a length of 2b. Major axis, horizontal or vertical, and then vice versa for the minor axis. And of course the length of the minor axis will be 2b, which is the covertices. Then the number a is called the semi-major axis, and the number b is called the semi-minor axis. Again, most of the time we just refer to these as vertices and covertices. And in fact, most books just go with that. But most of the time conics are taught at the Algebra 2 level as well. So we're trying to get a little bit more of the vocabulary here as well. Semi-major axis is the number a, and the semi-minor axis is the number b. Ellipse is centered at 0, 0. We have ourselves a nice little table here to pull this all together. But again, it's going to be really visual. You know, we're going to draw what we know. And that way it'll be easier to figure out where the foci are and get a good idea of that c squared equals a squared minus b squared relationship when we're missing the foci. So things to focus on. Find a, and a squared, because a squared needs to be bigger than b squared, so a is always bigger in ellipses, to figure out if you're horizontal or if you're vertical. And of course that's going to change your focal axis. If it's horizontal, well then your focal axis will be the x-axis, because we're going to start off centering these at 0, 0. And if it's vertical, then the y-axis is going to be your focal axis. And the rest of this we can find visually. Again, kind of new vocab here for vertices and covertices. Semi-major axis is A, and semi-minor axis, or covertices, are going to be B. And because it has a plus in the formula, if anything is missing, it's c squared equals a squared minus b squared. So let's get busy. Example 1 says finding the vertices and the foci of an ellipse. And it says find the vertices and the foci of the ellipse 4x squared plus 9y squared equals 36. And I look at that and I think, well, that doesn't have any of the characteristics that an elliptical formula is supposed to have. It's supposed to be division, division equals 1. Oh, well, I can make that happen. If that has to be a 1, I'll have to divide everything by 36. And then I'll do a little reducing. So now I know what's going on, and I find a, and I notice that 9 is bigger than 4, so that means a squared is 9, which of course means that a is going to be 3. So a plus or minus 3 for that because we're taking the square root. Let me get that a little bit separated there. All right, and then b squared would be 4, so b is plus or minus 2. So now I noticed that a was under the x squared, and that tells me that this is a horizontal ellipse. And that means I have to take the bigger value, which is a of 3, and go horizontally from a center at 0, 0. So 3 to the right and 3 to the left from 0, 0. Those are my vertices, also called the semi-major axis. Then my covertices have me going up and down 2 from 0, 0. So there are my covertices, or the semi-minor axes right there. And if I want to graph this, well, that's all I need. Now I have to do the hard part, which is try to make it look kind of circular. There we go. So try the best you can to get it to look circular. Absolutely don't connect them up with straight lines. That is a diamond. That is not going to be an ellipse. So do the best you can and try to get a nice oval out of that. So find the vertices and the foci of the ellipse. Well, we've actually found the vertices while we were trying to graph this. So the vertices are at plus or minus 3, 0. And then we need to figure out, well, where would the foci be? Well, I'm also going to put covertices down here. Again, this book kind of ignores covertices, but we need them to graph. So there were our covertices. And now to find the foci, I need to use c squared equals a squared minus b squared. And I already had a squared and b squared when I started off with the black equation up here. So c squared equals 9 minus 4. C squared equals 5. C will equal plus or minus the square root of 5. And those foci are always on the major axis. So if we were to punch in the square root of 5 on our calculator, we would get plus or minus. And it won't let me write it there, so let me try up here. Plus or minus 2.236. So they are inside, which makes sense from what we know from the drawings that they gave us. They are inside and they are on that focal axis, that major axis that we have. So that means those foci are at plus or minus the square root of 5, 0. And we will leave that in the perfect form of the square root of 5. So there's our first ellipse. And again, we realize, well, there's a lot going on in ellipses, but it's not necessarily really hard, especially when we have it centered at 0, 0. Example 2, find an equation and graphing an ellipse. So find an equation of an ellipse with foci at 0, negative 3, and 0, 3. So I'm going to go ahead and graph those right now. And these were the foci. So I'm going to put a little F there. All right, so there's my foci. And I started thinking right away, well, that's C. So the distance from the center to those points is 3 units. Still have a lot to go, though. So it says the minor axis has a length of 4. So from covertex to covertex, we're talking about a length of 4, which would mean splitting that would give us 2 units. Now, the foci are always on the focal axis, the major axis. So our covertices are definitely going to go on the x-axis this time because those are going to be on the minor axis. And that tells me that B is 2. Now, what I need to figure out is what's a, and then I can get this thing graphed. So c squared equals a squared minus b squared, and 3 squared equals a squared minus 2 squared. 9 equals a squared minus 4, so adding 4 to both sides, we have 13, and then the square root, plus or minus the square root of 13 equals a. If I could simplify that, I would, but what I really need to know is what is that as a decimal, because I need to graph that. So it's plus or minus 3.606 for a. And that goes on that major axis, which is where the foci are at. So 1, 2, 3.6. And connect that up. Try to make it a nice smooth shape. Okay, not so smooth, but again, we're going to do the best we can to start off with and get our little ovals in there. All right, so find an equation of the ellipse. Well, we have to do that yet. Minor axis has a length of 4. Sketch the ellipse and support your sketch with a grapher. Well, any of these we could certainly just put in as y equals and take a peek at them. But what we really want to do is be able to graph these by hand. So let's put it all together. Obviously, this is a vertical ellipse. It is longer vertically than it is wide horizontally. So what we have to do is remember that that means we have x squared over b squared plus y squared over a squared equals 1. So we'll have x squared over, and our b value is 2, so b squared is 4, plus y squared over, and our a value is the square root of 13, but when we square that, we'll just get 13. So there is the equation for our ellipse. Now let's take stock here. Find an equation of the ellipse. Did that. Sketch the ellipse. Did that. Support your sketch with a grapher. Well, let me explain how you would do that. We would take x squared over 4 plus y squared over 13 equals 1. And we would solve it for y. So we'd multiply to clear out all of the denominators that we have there, and then we'd move everything over. You might want to go ahead and subtract x squared over 4 first. Up to you how you get rid of everything. So let's do y squared over 13 equals 1 minus x squared over 4. And then we could multiply both sides by 13. And we'll get y squared equals 13 minus 13x squared over 4. And finally, we'd take the square root and get plus or minus the square root of 13 minus 13x squared over 4. Now, this is one of the reasons I typically don't like putting these into the calculator, because we have more than one term in our numerator here. This is going to require a square root, and we're also going to need double parentheses there to get everything to work out the way we want it to. You might get away with just one set of parentheses there for your numerator, but you'd have to punch them both in. So you'd make y sub 1 equal to 13 minus 13x squared over 4, and y sub 2 equals negative square root of 13 minus 13x squared in parentheses divided by 4. And you do all that, and calculators will typically show a gap. It won't actually have your ellipse fully together. So what we do is the same thing that I talked about when we were doing parabolas, which is we try to center the parabola so that it will, or the parabola, center the ellipse so that it will meet. And in this case, if you don't want a graph for error, it's kind of a strange window. If you change to negative 9.4 to 9.4 by the y's there would be negative 6.2 to 6.2. Then the gap that's created by your graphing calculator will close itself off. So it's kind of like a little zoom in that it does, and then everything gets taken care of. All right, so we did everything. We wrote an equation, and we sketched the ellipse, and I've shown you how to do this, and if you want to punch it in, you can certainly go ahead and do that and take a look at the ellipse. But what I really need to get to here is the translation of ellipses. So this is when it's not centered at 0, 0 anymore. And that's going to be good old H and K that are going to help us out with that. So you'll notice the change to these is in the numerator. When an ellipse with center 0, 0 is translated horizontally by h units and vertically by k units, the center of the ellipse moves from 0, 0 to hk. Such a translation does not change the length of the major or minor axis or the Pythagorean relationship. So as we look at this chart, this new chart, again, this is something we're going to do that's very, very visual. We notice that we're still seeing the larger of the two numbers is a, and if that's under the x minus h squared, you have a horizontal ellipse. And if it's under the y squared, you have a vertical ellipse. So that has not changed. But now we have the h and k to move that center from 0, 0. Again, the rest of this, it's great that they have all these little formulas here, but this is very visual. So if we can just do some counting as we go through here, we can get all these pieces. And we don't want to forget, if we need the foci, we have c squared equals a squared minus b squared, because the original formula had a plus in it. All right, so taking a look at this figure, we can see that there is a new center now at HK. And like I said, what we're going to do is we're going to use that distance from the center to the foci, and we'll just do a little addition and some subtraction to see where those new spots are at. Same thing with our vertices. We'll use our new center and go a units right and left for the horizontal. And then for our covertices, our b value, we're going to go up and down from our center. So right here is our starting place. Vertically, just flip that around. You know, if we know that we have vertices that are supposed to go vertically, we're going to take our new center, and for the y coordinate, we're going to add our a value up and down. And then from our new center, we'd add our x values to get to those covertices. Again, A being the semi-major axis and B the semi-minor axis. So once we get it drawn, it doesn't look as bad as all of this. We need to start getting a sketch and put this all together. So to graph or write an equation for an ellipse from these features, sketch and label what you have. Locate and plot the center. Going to be halfway between the foci, halfway between the vertices, halfway between the covertices. Determine A, B, and C. Mark those on the graph. Then sketch the ellipse, trying to round it off, and determine which direction it is, horizontal or vertical. And once you know if it's horizontal or vertical, well then, of course, you can go ahead and write an equation for it. And that's the next place that we would want to go, is writing the equations for these translated ellipses. So finding an equation of an ellipse. Find the standard form of the equation for an ellipse whose major axis has endpoints at -2, -1, and 8, -1, and whose minor axis has a length of 8. Well, if these are the endpoints of the major axis, that makes them vertices. So we would want to put those on our graph at -2, -1, and at 8, -1. And halfway between those two is going to be where the center is. So I'm going to write down these coordinates and realize, well, they both stay with -1 on the y's. What I really need is halfway between -2 and 8. So -2 plus 8 divided by 2 would be the average, and that's how we would find the new x coordinate. So that's 6 over 2, which is 3. So our center is at 3, -1. So there it is. I just found h and k. H is 3, k is -1. While I'm at it, let me figure out what a is. So a is going to be the distance from the center to the vertices. And we had a 3, -1, and an 8, -1, which is a distance of 5. So my a value is 5. Now let me keep reading and see if there's more information. Its minor axis has a length of 8. Well, that tells me that if I split that, that's how far I'm going to have to go up and down. So from my center, I have to go up and down 4. And these are my covertices. So we are at 3, 3, and 3, -1, 2, 3, 4, 5. And of course, halfway between 3 and negative 5, we could take 3 plus negative 5, which is negative 2, divide it by 2, and we would get negative 1. So our center is exactly where it's supposed to be. Now, what this helps me know, and I did know it after we had the vertices up there, is that this is a horizontal ellipse. And we want to write the standard form of that, so that's going to be x minus h squared over a squared plus y minus k squared over b squared equals 1, because when that a squared is underneath our x coordinate squared, that's the horizontal. So we want to go ahead and write this if we have everything that we need, and it turns out that all we need is a and b once we have that center at 3, negative 1. So this is going to be x minus 3 squared over, and my a value was 5, so 5 squared is 25, and we did use the fact that we had a b value of 4 to go ahead and figure out that the minor axis had a length of 8. We split that in 2, so y minus a negative 1 would be y plus 1 for our k value, and 4 squared would be 16. So x minus 3 squared over 25 plus the quantity y plus 1 squared over 16 equals 1. Find the standard form of the equation for an ellipse whose major axis has endpoints at those two ordered pairs and whose minor axis has a length of 8. And then I probably wouldn't be able to help myself. I'd have to try and round this out. Now I do want to tell you that one of the tricks that I use as a not necessarily artsy person here is to first make a dashed or a dotted ellipse and then kind of look at where things don't look like they're perfect and smooth it out a little bit. So if you're really, really bad at it, that's one of the things you can try, is dashed or dotted first and then kind of fix your way through as you go through. So we've written it and we graphed it. Example 4 says, let's figure out locating the key points of an ellipse. Find the center, the vertices, and the foci of the ellipse. And one of the things that I notice is a squared is underneath the y. So this is going to be a vertical ellipse. And that also tells me, since a squared is 49, that a is going to be a plus or minus 7. Might as well do the same thing with my b value right now and get the plus or minus 3. And then, if I want to graph it, the other thing I'm going to need to know is the center. And that's h and k. So if we have x minus h squared plus y minus k squared on the top, then that gives me an h value of negative 2 and a k value of 5. So there's my center at negative 2, 5. Put that C for center right there. I know it's vertical, so I want to go a units up and down. And a happens to be plus or minus 7, and that's going to take me off the grid. So I'm going to have to change this and go by 2's. So now I'm going to go to my negative 2, but then up 2, 4, 5, right there for my center. And my a value of 7 up and down, there's 1, 3, 5, 7, 1, 3, 5, 7 vertices, and then side to side I need to go 3 units for my covertices. And again, one of those things to try to help you when you're first drawing your ellipses, dashed or dotted, so you get a good sense of where everything is going to go. So let's go ahead. We've got the center and we know where the placement of things are. We just need to put the math together. So we were at negative 2, 5, and we had to go up and down 7 units. Well, we were at 5 on the y's, and if I take 5 minus 7, I'll be at a negative 2. So even without going to graph, you could just kind of do the math. And then I was at 5 and I had to add 7, so that would be negative 2, 12. So there are the two vertices. And then they also wanted us to figure out the foci. And that we don't have up here yet because we haven't found c. So c squared equals a squared minus b squared. And c squared will equal 49 minus 9. C squared equals 40. So c equals plus or minus the square root of 40, which this time we can simplify. Square root of 4 times the square root of 10. So c equals plus or minus 2 square roots of 10. And I just need to figure out, well, where would those go? Well, like the vertices, the foci have to be on the major axis. So they're going to be somewhere in here. And that helps me figure out that, all right, I'm still going to have to add to the y that I had for my center. So for my foci, I have negative 2 and then 5 minus 2 square roots of 10 to make it go down, and negative 2, 5 plus 2 square roots of 10 to make that go up. So now we check and see if we've done everything. Find the center. We have that listed at negative 2, 5. Find the vertices, negative 2, 12, and negative 2, negative 2. And then our foci at negative 2, 5 minus 2 square roots of 10, and negative 2, 5 plus 2 square roots of 10. And again, it's all graphed, even though they didn't ask us to do that, just so we can get a little extra practice with that. So that is the end of day 1, and like I said, that pretty much covers our objectives up to the application piece. And there is your assignment for 8-2 day 1. And ellipses are kind of fun to graph, so even though you're not going to be perfect at them to start with, except for those of you that are art majors, go ahead and just give it a try. Like I said, use the dashed or dotted to help yourself get everything that you need there. So have some fun with the conics.